Hello, today we are going to learn about state space representation from chapter 3. This is something new. Previously we have been learning about the transfer function, and this transfer function is defined in Laplace domain, or we can say frequency domain. So transfer function is a characteristics in a frequency domain for a given system, whereas the state space is a mathematical description or characteristic in time domain. Okay, so this is the difference between difference between transfer function and state space. Transfer function is defined in Laplace domain or frequency domain that define the relation between output and input. Similarly, state space defines the relationship between output and input in time domain, not in frequency domain. Okay, so we are coming back to time domain again, but in this case, instead of using simple differential equation, we will use a special set of differential equation that is called a state space. Okay, so we will learn this modeling in time domain. That means we will define the relation between input and output, which is called state space. Now we will start with simple RL circuit, series circuit. There is a current I, okay, and for this circuit, if we apply the KVL, the relation will be like this: VR plus VL is equal to V, okay, and VR is nothing but R into I, and VL is nothing but L into di by dt. Okay, so we know these basic things from the circuit theory. Now this is a differential equation that defines the output I, the relation between output I and input V. Okay, so this is the input output relation. Now we are going to rearrange this equation in a special format that is called state space. So state space is basically the differential equation, but in a specific format. So let's see. In a state space representation, at first we have to define a state variable. For example, we can assume I is a state variable, okay, but the variable can be something different than I. It can be VR, it can be VL, etc. Okay, so at first we will define a variable I. Okay, so and then we will define the derivative of di through a equation which is called state equation. Okay, so we are going to write this di by dt from this basic equation. We can rewrite this equation into this one, so that we get the di by dt. Now there is some restriction. We cannot write this equation in any format. So the rule says right side of this di by dt equation should contain only the input and state variable. That means I is the state variable and V is the output. So we cannot use any other variable other than state variable and input variable, but it can contain some constant parameter like L, R, etc. Okay, so that is the rules for a state equation. So we get at first we let a variable, state variable, and then we write the equation for that variable, derivative of that variable di by dt. Okay, finally what we need is output equation. For example, the output for this system can be VL, can be VR, can be I, anything can be output. It depends how it is defined in the question. Okay, so let's, for example, let us assume that the output is VR. So VR is the output. So now we have to write the equation for VR using the same rules here. That means we can only use state variable and input. So in this case we know the VR is nothing but I into R, so that is enough to define the output equation. Okay, so output equation is simply VR is equal to R into I, so there is no need to include V here. So now if for example our output is VL, we can write it from here that VL is nothing but V minus VR, which is V minus R into I. But in this case we cannot write like V minus VL. We cannot use VL here because VL is not a state variable. We have to convert or rewrite the VL into RI. So that is the rules for StateSpace equation. So in our StateSpace representation, we have to follow three basic steps. First one is state variable, second one is state equation, which is the derivative of the state variable, but the right side should contain only state variable and input. Similarly, the output equation should contain only state variable and input. No other variables is allowed in the equation. Okay, so these three parts we will always use these three steps. Now let's go for three component RLC circuit. RLC, in this case if we find the transfer function for this circuit, we will see there this is a second order transfer function and we call it second order system. So for second order system we have to actually use more state variable, that means two state variable. Now let's try this. So we first of all we need to recall our basic equation or relation between the circuit components. For example, this is the Kirchhoff's voltage law. This is VL plus VR plus VC is equal to input V. This is the KVL, and we have to remember the basic relation between charge and current. For example, dq by dt is equal to I, etc., etc. So we have to remember all this formula. So now let us try to write a state space equation. In this case, this is a second order system, and we have to assume we have to take two state variables. So in this case we will try to use two variable I and Q, but you can start with different set of state variable, no problem, but we will learn that gradually. Okay, so for now let us focus on using I, this series current, and Q, whatever charge is going through this circuit. Okay, so now we have to write two equations. One is dq by dt and another is di by dt, because we have these two state variable, right? So dq by dt, we know that dq by dt is equal to I, so we put it I here. Now we have to ask if I is a state variable or not. Is it? Yes, this is a state variable, so we do not need to rewrite this anymore. This is a state equation. dq by dt is equal to I. That's it. That's our state equation, first equation. Now, second equation is we have to write the equation for di by dt. So, for di by dt, we can write the equation from using this KVL. So, di by dt is nothing but is equal to 1 by L, and everything can be shifted on the right side. So, what we will have is 1 by LC Q. This is Q. Integration of I is nothing but Q. So, 1 by LC Q minus R by L. This is R by L into I, and 1 by L into V. So, we just rewrite this equation into this format. Now, we have to ask ourselves that if this equation contain any other variable other than state variable and input, let's check. So, first variable is Q. Q is our state variable, I is our state variable, and V is our input. So, it complies with our rules. So, if it complies with the rules of writing a state equation, then it is done, it is finished. If there is any other variable other than these 2 or 3, then we have to rewrite or replace those variables with state variables. Okay, so this is what we have to remember. And also, the right side of this state equation cannot include any derivative or integration term, like this one integration, or like this term derivative. We cannot use those things. This will be simply linear combination of state variable and input. So, that's our state equation. So, we have 2 state variable and 2 state equation. Now, let's go for output equation. For output equation VL, we have to use the same formula or rules as we use for a state equation. That is, we have to use the state variable here, Q and I, and input. So, let's see how we have written this out. So, this VL is nothing but this one, right? This whole term. We just written down the equation for di by dt, and VL is nothing but L into di by dt. So, everything on the right side will be the equation for output. So, that is 1 by C Q R into I plus V. So, this is the output equation. So, that's it. That's our state equation and output equation. Now I hope you just getting familiar what is the state equation and output equation. So, these 2 set of equation defines the state space. Okay. Now, we will use a special format. Now, here we just rewriting these 2 equations into a matrix format, just like we did in applying Cramer's rule in chapter 2, right? So, we are rewriting these 2 equations into a matrix format. Here, Q dot means dq by dt. So, dq by dt is nothing but I. So, you can see that this equation is appearing in this matrix format. How? The Q dot is equal to nothing but 0 into Q, 1 into I. We know how 2 matrices get multiplied, and this column will be dot product with this row. So, Q into 0 plus I into 1 plus V into 0. So, in this way we can see that this Q dot equation appearing from this equation. So, you can see there is no other term, just I. So, you can see the same thing here, the I into 1, and you can see that Q into 0, because there is no term Q here and there is no V term here. So, V into 0. So, in this equation matrix format, we are observing which term contain what coefficient. For example, Q term contain no coefficient here 0, I containing 1 and B containing 0. Okay, so this matrix tell us everything about this equation. And then again here we can convert this equation to this for example, Q contain 1 by LC, which is appearing here, and I contain minus R by L, and B contain 1 by N, etc. So this is how we rewrite this equation into the matrix format. So this is our final format of state equation. Okay. Similarly, we can rewrite the output equation in this similar format. You can see that state variable into something and input into something. So similarly here you can see that Q into 1 minus 1 by C is appearing here, Q into 1 by C, C minus I into minus R plus B into 1. Okay. So this is our output equation. Okay. But this output here we have only one output, but StateSpace can have multiple output. In that case, it should be a column vector y1, y2, and there should be more than one row here. There should be more than one row here as well. We will see that later. Anyway, so for this example, these two equation is our StateSpace model, and this is the state equation, this is the output equation. Now, we have some name for these matrices. For example, this state equation in general can be concisely represented using this format: x dot. X dot means a number of derivative of state variables, which can be x1, x2, etc. These are the dot. Dot means derivative. Okay. And here we can see a matrix A. So this is the A matrix, and x means these variables x1, x2, or q, I, etc. Similarly, this is B matrix, and this is the input u. Okay. Similarly, for output equation we have y is equal to cx. C means this matrix, x means this one, and u means this one, and u means this one. So in this case, it is not always the case that this will be one element. It can contain multiple columns if there is multiple input. It can have multiple rows if there is a multiple output. Okay? So in that way, if the number of input increases or number of output increases, there will be more column and more rows. Anyway, so we have the name of for all these matrix and variables. X is the state vector, x dot is the derivative of the state vector, y is the output vector, u is the input, and A is called system matrix, B called input matrix, this is the input matrix, C is called output matrix, and D is called feed forward matrix. Anyway, the names are not important. Let's go to the next example. So we will repeat our previous example, but now we will use different state variables. So previously we have used I and Q, but now we will use different variables, for example BC and I. Okay, but you have to use two state variables, not three, not one, but two, because this is a second order system. We will talk about that later. So once again, we have to remember the basic laws like Kirchhoff's voltage law, VR plus VL plus VC is equal to V, and we have to remember the basic voltage current relationship. For example, for capacitor it is C into dV by dt is equal to I. For inductor, L into di by dt is equal to V. and for current it is I into R is equal to V. So we have to remember all this relation. Now let us try to write state equation. How many state equation? Because two variables are here, we have to write two state equation. One is dvc by dt in terms of state variable, for example vc into something plus I into something plus input into something. Okay, we have to write the state equation in this format. And another one is for this I we have to write di by dt. Okay, and also we have to write the output equation using the same format, vc into something, I into something, and v into something. Why? Because these are our state variable, that's why. But you don't have to find something I here, because it can be 0. There can be no I here for this equation, so we will simply put 0 here, nothing else. Okay, so I will let you practice. I gave the framework and the restriction, so you should fill this up. How can you fill this up? You can use the basic laws, for example VC here, right? For example you have the dvc by dt. From this dvc by dt you can write 1 by c into I, right? And I is the state variable, so you use this equation to write the dvc by dt. So you can get something here. So this should be 0, this should be 1 by c, and this should be 0, something like that. Okay, similarly di by dt, look in these equations. Okay, for example if you look di by dt, look the solution of di by dt, you cannot use this one because di by dt is equal to VL, 1 by L into VL, but VL is not our state variable, so you cannot use it. Instead you can use this one. Okay, because the VL is equal to V minus VC minus VR, and VC is the state variable and VR can be replaced with I. So use this equation to write this equation. Okay, and once you're done with this, and similarly you can also write the equation for VL from this KVL equation, and after you just try to do it yourself. You can pause the video if required. Once you're done, you can go to the next format, which is in matrix format. For example, the state equations should be written in matrix format. One is VC dot I dot is equal to something like this, and then rewrite the output equation in the matrix format, which is y is equal to something like this. Okay, so try to do it yourself. This is the example of actually book, but you should do it by yourself. If you are done, then only then you go to the next site. So now we will discuss about the number of state variable. How many state variable there should be? For example, a state variable is always equal to the order of the differential equation. If it is second order equation, then the number of state variable should be 2. That's it. If it is third order, then it should be 3, like that. And we can also determine that from the order of denominator of transfer function. We know this order of denominator, from this, using this order we can find the order of the transfer function or the order of the system. So you can use either of this, or there is another information when you are solving the circuits. For circuit, the number of independent energy storage element can also indicate the number of state variable. For example, you can see that we know the inductor and capacitor are the energy storage element, right? So in this circuit there is only one element, one such element, so the order is 1. In the second case, there are 2 energy storage elements, so the order is 2. And the third case, for example, in this example there is 3 elements, so the order is 3, so we should use 3 state variable to solve this problem. It's time to practice. So let's solve this circuit. Here we can see there are 2 energy storage elements, so it should be 2 state variable. So now the next question is how we are going to define the state variable at the beginning. It can be IR, it can be IC, it can be IL, it can be VL, it can be anything, right? Which one is easier for the circuit? So I'm going to tell that. So for circuit we have a voltage current relation for capacitor and inductor, and you can see 2 terms here. One is dVc by dt and another one is dIL by dt, right? So if we assume that Vc is our state variable and IL is our state variable, then we have a advantage that we can start writing the state equation right from here. For example, we can start writing state equation using this equation, for example dVc by dt, di by dt. That will be our state equation. We'll see in this example. So for circuit, if we always follow these rules, that for capacitor the voltage can be state variable and for inductor the current can be state variable, if you follow this will be the easiest way to start your math. Okay, this is the easier start, but you can do it otherwise, no problem, but this is the easiest way to start. So for capacitor we will assume the voltage is the state variable, for inductor we will assume the current is state variable. Why? Because we have to write 2 state equation, one is dVc by dt and another is di by dt, and we can start writing equation using this basic relation, which is 1 by C into IC, 1 by L into VL, right? Okay. Now what we have to do next? If you check this equation, you can see that this IC is not state variable and this VL is not state variable, so this is not the final format of a state equation. What we need to do now is replace this VL and this as well. So how do we do that? We can do that using our circuit formula, that is KVL. For example, in this case, for example, in this case, we can assume that DC is equal to VR, which is equal to IR. So you can get this kind of relation, and also you can say IL is equal to IR plus IC, and we can write VL is equal to V minus VR or VC. VR is equal to VC, right? So you can write a KVL equation here. V is equal to VL plus VC. So we can write all these equations from the circuit using KVL or KCL or Ohm's law, like VR is equal to IR, or VR and VC are there. Because these two are parallel, they should be equal. So we can use all these equations to replace IC using these 2 variables. Can you do that? Similarly, we can replace VL with this VC and IL, and also with V. I hope you can do it yourself. For example, if you look at VL is nothing but, here you can see, if you take the KVL, you can rewrite VL in terms of V and VC. Okay, so you can easily write the equation VL is nothing but V minus VC. Okay, so you can rewrite this equation. Similarly, IC can be replaced with IL minus IR. Okay, and this IR can be replaced with VR divided by R, and VR can be replaced with VC. So in this way you can convert the equation in this format. All of you should follow this. So finally, if the question defines that IR is the output, you can write an equation for IR in the similar fashion. Okay, and in our final stage we will rewrite these two equations in the matrix format. Please do it yourself, and similarly you should rewrite the output equation. Okay, now it's time for practice more. Please try to solve this circuit. I think this will be a little bit tough because this is something involve three different state variables. You can see three energy storage elements, so there should be three different variables. One should be VC1, another should be VL, and another should be VC2. So try to do it yourself. Okay, no more today. It's